Hello, welcome to this video produced as part of the Further Maths Support Programme's material for A-Level Maths in Further Maths. This one focuses on the basic principles of elastic potential energy. We've already discussed energy stored. It can have two forms. We're interested particularly here in gravitational potential energy as a comparison, but there's also kinetic energy. If a spring is stretched or compressed, there's energy stored in the spring. Now we know this from the idea of winding up an old-fashioned clockwork clock. You turn the effort into turning the winding mechanism, it stores the energy in a spiral spring inside the clock, and that's released by propelling the clock into motion over the hours that follow. Similarly, if you draw a catapult back with a pellet, it's an effort to do that, and the effort that you make is stored as potential energy in the system, and when you let go, that potential energy realizes itself as the kinetic energy of the pellet. Now we refer to energy stored in that way as elastic potential energy. So how are we going to get some idea what the quantification of this? Let's suppose that you've got a spring and you draw it out this way. Now the string will resist, so there'll be a tension in it, and you'll be exerting a force F. How much bigger does the force F have to be than the tension? Well, it has to be bigger certainly, but it need be arbitrarily small, the difference, since we're not really interested in how long it takes to do it. Because it's arbitrarily small, we can take a limit and say in the end it amounts to saying that the work done that you have to do is the same, the force can be considered the same as the tension as a result of that limit. So if we're to work out what the work done is in extending a spring, we can do it by assuming that the force that you need will be the same as the tension in the string. So that will mean then that we have to recourse to the expression we've got for the work done by a variable force, and we know that that force comes from Hooke's law. So if we put the Hooke's law expression into the integral, there it is. We have to use a different letter for the variable of integration to the one that's in the limit, but that's a minor point. If we do the integration, we see that you're integrating x dashed essentially to x dashed squared over 2, and then put the limits in. Our final expression is lambda x squared over 2l for the work done that we do in storing this, in stretching the spring or string, or you can look at it as the energy that's stored. So that's the expression we're going to use. Now that work done in stretching isn't wasted, it's stored up in the spring. That's the whole point. That's why it's called potential energy. So we can use the work energy principle now using that energy expression as well as gravitational potential energy and as well as kinetic energy, so long as we are careful about what other forces may be acting. And remember, this is a pretty generous situation, because if you look at circular motion, there are certainly forces acting there which are not necessarily conservative, don't have potential forces, but we can argue that they don't contribute because they don't do any work. So with this little care, the idea of using energy can be quite extensive. The situations in which energy can be used can be quite extensive. So there's our expression, lambda x squared over 2l, and in mechanical systems we treat that in a similar way to gravitational potential energy. We can work out energy released by asking what the difference of the extensions, what the two extension values are, and working out the difference in that energy expression. Right, let's begin by applying the formula simply. You've got an elastic string of natural length 1.5 meters, elasticity 50 newtons, length stretched to a length of 2 meters. Now the units are consistent, so we can leave them out. L is equal to 1.5. The extension is equal to 0.5, not 2. It's the difference between the new length and the old length, and the modulus of elasticity is 50. And those are the expressions which we'll use in our expression lambda x squared over 2l to get the stored energy. Okay then, here we go. That's what I've just said, and here's the application to the formula. We put the numbers in, and it's really very simple. You get this 0.5 squared from the 0.5, and we end up with our final answer 4.17. Since the well, as usual, I've put in my calculator displays until I got lazy and put dots, and I've shown enough to show how I've got the rounded value, and then I finally put a statement in context with the units. The units will be joules because we consistently use meters and newtons. Right, another example. Now here we've got a slightly more complex situation. We've got a spring on a table. Now it's a smooth horizontal table, so we don't have to involve friction, but we certainly do have to involve gravity and the normal reaction. So our first challenge is a force diagram. There it is. There'll be a tension in the spring, and there'll be a force which is exerted to get the spring to extend. And as we argued before, we can regard F as being the same, equal in value to T, because it can be arbitrarily close to it. I haven't shown forces up and down because if we're moving horizontally, those two forces will do no work since the movement is at right angles to them. I said I hadn't shown them. I have shown them, but I haven't given them letters, and that's simply so that I realise I have to argue that through, that they don't contribute. Righto, we can put some quantification into this then. We've got the formula, and from the information, as usual, we've got this data summary. The lambda is given as 180, the units are consistent, the L is 0.4, and remember, as before, the X is not 0.55, but the difference between the extension and the natural length expressed in metric units, so 0.15. If we do that, then the energy expression will be in joules, so we work it out. Calculator gives us an exact answer in this case, and we can say finally in context that the work done is 5.06 joules. Well, that brings us to the end of that presentation. The next one will be on more complex problems using conservation of energy.